All right, so this is your lesson on 12.4. 12.4 continues our work with circles, and it can be a bit of a tricky lesson for many students, so please make sure you're paying attention to all the cute ways I teach you to remember the theorems in this lesson. Let's first talk about angles. There are many angle relationships formed by lines inside circles, so let's start talking about ones where lines intersect inside of circles. Here's my first theorem. If I have two lines that intersect inside my circle, and that's going to be a key point in this topic right here. We're inside the circle. Then the angle that is created by their intersection, this guy right here, is called angle 1. The measure of angle 1 is essentially equal to the average of its two arcs that it intercepts, okay? So what I look at here is the lines intersected and created angle X and angle Y. I should be calling them arcs. So what I would do to find the measure of angle 1 is I add x and y and divide it by 2. That's why I look at it as the average. Another way that I like to think about this is because I'm intersecting inside the circle. When I'm inside my circle of friends, I feel positive. So because I feel positive, I'm going to add x and y and divide by 2. I'm emphasizing this positivity because there's also some negativity that happens when two lines intersect outside of the circle. So now let's talk about being outside the circle. Anytime two lines are created and intersect outside of the circle. So here's angle 1 outside the circle in 3 different scenarios. Okay? It is also going to be looking at the two arcs that it intersects. So we have arc measure x, and we have arc measure y. Now, rather than adding x and y and dividing by 2, we're going to subtract x and y and then divide by 2. So it's kind of like the opposite of taking the average. And the way I like to remember this is because when I'm outside of my group of friends, I feel very negative. I feel very sad. So when I'm outside my friends, I subtract. Okay? So I'm going to subtract the big arc and the small arc, and then I'm going to divide by 2. And it's always in relation to, once again, the arcs that we intercept by the lines. Okay? Now, what are these lines called? These lines are called secants. Secants are lines that intersect a circle in exactly 2 points. So here is secant line AB intersecting circle O in exactly 2 points. So that is the purpose of these 2 theorems, talking about the angles created by secants. All right, so let's find some angle measures. So in the first scenario in question A, I'm noticing that angle X is an angle created by 2 lines that intersect inside the circle. Now I also want to point out the fact that because I do not see the center, I am not dealing with a central angle. Recall from chapter 10, if I have a central angle, it's simply equal to the angle measure's arc, okay? This is not the situation. X is created by 2 secant lines. So to find the measure of X, what I'm going to do is I'm going to take the average of the 2 angles, okay? The 2 angles that I intercept would be a 46-degree arc measure and a 90-degree arc measure. So I'm going to take half of the sum of 46 and 90. And this is just me showing my work right here. All right, so order of operations says that we should first work inside of our parentheses. So we should first do 46 plus 90. And 46 plus 90 gets us 136. So I need to take 1/2 of 136. So when I take 1/2 of 136, that simply gets me a measurement of 68. So the measure for X is 68 degrees. So now I'm looking at question B. Question B, I'm noticing that I have an angle formed on the outside of my circle. And like I talked about before, when I'm outside my circle of friends, I'm kind of feeling sad. I'm feeling rather negative. So the measure of 20 degrees was created on the outside. So 20 will be equal to half, and what I'm going to do is I'm going to subtract the 2 arc measures that were intercepted. So my big arc is 95. Big number is always going to have to come first. So 95 goes first, and the second arc that I intercepted had a measure of z. So notice now in this situation, I am solving for z. So the first thing I'm going to do to solve this equation is divide both sides by 1/2, which is the same thing as multiplying both sides by 2. So that gets me 40 is equal to 95 minus z. Now to isolate my variable z, all I got to do is subtract 95. And when I subtract 95, I get negative 55 is equal to negative z, which tells me if I divide both sides by -1, 55 is equal to z. So let's see you get some practice with these concepts. Here are 3 got it problems. All right, let's check your answers. So answers that I'm looking for, so please make sure you're checking your work. W was 250, Y was 40, and X was also 40. So please take a look and pause if you need to. I do want to point out that W could have been solved in other ways. Please recall that the full rotation around the circle is 360 degrees. And because I know that part of my rotation from here to here is 110, all I got to do is subtract 110 degrees from my total rotation to find that W is indeed 250 degrees. So let's make it a word problem here. A satellite in a geostationary orbit above Earth's equator has a viewing angle of Earth formed by 2 tangents to the equator. The viewing angle is about 17.5 degrees. What is the measure of the arc of Earth that is viewed from the satellite? All right, so what we are going to do first is we're going to recognize what I don't know, okay? I do not know this arc right here, okay? That is my goal. I'm trying to figure out the measure of the arc of Earth that's viewed from the satellite. And from the satellite, that is what I can see. But you know what I also don't know? I also don't know this measurement here. But like we talked about on the previous Got It, we can recall that full rotation would be 360. So I can create the expression 360 minus x to find this other piece right here. So now that I know that this other piece is 360 minus x, I can create that relationship that exists between angles that are outside of the circle as well as its intercepted arcs. Okay, so the angle outside my circle has a measure of 17.5, and I know that it is equal to half of the subtraction between its 2 intercepted arcs. Now its bigger arc is 360 minus x. And remember, when I'm outside my circle, I feel negative, so I'm going to subtract the measure of its smaller arc, which is x. Okay? So here is my expression to deal with. So the first thing that I can do is multiply both sides by 2 or divide by 1/2, whichever way you want to look at that. So that gives me 35 is equal to, that got rid of the 1/2 on this side, so 360 minus x minus x. And if I combine like terms, that really gets me 360 minus 2x on the right-hand side. And so then all I need to do is subtract 360. And when I subtract 360, that gets me negative 325 is equal to negative 2x. And when I divide both sides by negative 2, that gives me a final answer of 162.5 degrees. And yes, that is an exact answer because I did not have to round. Now that's approaching this problem using the methods shown in 12.4. But I also want to remind you about the methods that we learned about in 12.1. Notice in this question it talked about the fact that I had 2 tangent lines. And what we talked about in the very first lesson is the fact that tangent lines are going to be perpendicular to the radius, okay? So if I kind of just recreate this picture for just a second here, and then I'm going to draw in for myself 2 radii. What I know is I'm perpendicular, so now I can add in 2 right angles. And if I already know that this is 17.5 degrees, all I got to recall is the fact that I have a 4-sided figure. A 4-sided figure adds up to 360 degrees. degrees. And because I already know two of my angles are 90, we'd have 90 plus 90 plus 17.5. Then I could solve for x. Now x would be this angle right here, but notice it is a central angle, and therefore it is the same measurement as its arc across from it. So I want you to think about the fact that you have two different ways actually to approach this particular problem. So make your choice. What way would you like to go? Here's your got it. All right, so here's the solution we are looking at. We're looking at a 160 degrees for part A, and here's a thought for reasoning question. Is the probe or geostationary satellite in problem 2 closer to Earth? Explain. The probe is closer. As an observer moves away from Earth, the viewing angle will decrease. It's going to get further and further away, making the measure of arc getting larger and larger, approaching 180 degrees. So those were our angles. So let's talk segments, okay? All right, there are three different scenarios that can happen when segments or lines intersect inside or outside a circle. Here's case number one. Case number one, I like to refer to as the piece case, okay? And so what I refer to this one as is piece times piece equals piece times piece. And I have to make that a little bit smaller because I kind of just enlarge my entire font here. But here's where I get that from. To find these values here, I'm going to take piece A and multiply it by piece B. And that's going to be equal to piece C times piece D. So piece times piece equals piece times piece. All right, that's case one. Let's talk case two. In case two, I have pieces on the outside of the circle, okay? So here's what I think about when I see this one. Outside times whole is equal to outside times whole, okay? So let me write that one down. Outside times whole is equal to outside times whole. That's the scenario that I'm thinking about when I see a situation and I have two segments that have a piece sitting out on the outside. Here's the final situation. In the final situation, I have a tangent and then a line that's on the outside and the inside of the circle. So here's how I look at this one. Tangent squared is equal to outside times whole. So let me write that one down. Tangent squared is equal to the outside times the whole. Once again, these are just how I'm remembering these particular theorems. Now you'll see right here that this is actually how the textbook reminds you of these theorems. And notice that it just utilizes the terminology associated in geometry, like chords and secants and tangents. So I have my three. Piece times piece equals piece times piece. Outside times whole equals outside times whole. Tangent squared equals outside times whole. So let's try out two examples. All right, so my first example, I'm noticing I have two segments that have an outside piece as well as pieces on the inside. So I'm falling under the second category here of outside times whole equals outside times whole. So that's what I'm going to think about. The outside times whole equals the outside times the whole. And I'm going to write that down on my paper right here. Outside times whole equals outside times whole. So now I need to think about which is what. The first outside that I see has a length of 6. Now I need to think about the whole length of that line. So the whole length of that line would be 6 times 8. I'm sorry, 6 plus 8. Ooh, bad time to be doing math. It's already, well, it's only 6:55 in the morning here. All right, so that's my first chunk. Now I need my second outside. My second outside has a length of 7. Now I need the whole. Now this is where my variable comes into play. I have a y. So the whole for this situation is going to be 7 plus y. And now all I need to do is start to simplify my problem here. So So first I'm going to do 6 plus 8, and 6 plus 8 gets me 14. 6 times 14, that gets me 84. So 84 is equal to, I'm going to distribute the 7. We have 49 plus 7y. So then I'm going to subtract 49 from both sides, and that gets me 35 is equal to 7y. Divide both sides by 7, and I get 5 is equal to y. So now I'm looking at my second problem, and I'm noticing that I have a tangent line. And because I have a tangent line, I'm falling under the category of tangent squared equals outside times whole. So I'm going to just write that down really quickly when I see that problem. That way I have a little bit of a reminder. All right, here is my tangent. My tangent is z, so therefore I have z squared. So tangent squared is equal to outside times whole. The outside length that I have is 8. The whole length that I have would be 8 and 16, so we have 8 plus 16. So now all I got to do is start to simplify my problem here. Well, 8 plus 16 gets me 24. So we have z squared is equal to 8 times 24 gets me 192. So then I'm going to take the square root of both sides. Now, side note, you should be putting a plus or a minus, but because z represents a length of a segment, we're only worrying about the positive root. Now, this is why we've been practicing simplifying square roots since the very first day of class. All right, so I need two numbers that multiply to get me 192. Well, the first two numbers that popped into my head were 16 and 12. Because I know when I see square root of 16, I can pull out a 4. But then I see square root of 12, and I'm like, oh, gosh darn it, I can go further. The square root of 12 breaks into the square root of 4 and the square root of 3. Well, the square root of 4 is 2, so now I can pull out a 2. So I have 4 times 2 times the square root of 3, getting me an answer of 8 square root of 3. Here is your final got it questions. And I even wrote down what I wanted you to know. Outside times whole equals outside times whole, and part times part equals part times part. All right, here is the work for my two got it problems. We should have an answer of 13.8, and we should have an answer of 3.2. So this was your lesson for 12.4. Please feel free to rewatch anything you'd like, and if you'd like to get a start on Math Excel, you are more than welcome to. Have a great day.